The paper we're diving into today is called Adversarial Flow Models. And if you're just looking for the 1-minute summary, here are the key takeaways. For a few years now, generative modeling has had this painful trade-off. You could get the single-step speed of a GAN, a generative adversarial network, but you totally sacrifice training stability. Or you get the stability of flow models like diffusion, but then you're stuck with all these slow, iterative inference steps.
Right. And what adversarial flow models, or AF models, do is they actually merge these two worlds. They keep the adversarial objective, which is great for matching distributions, but they add an optimal transport loss constraint. This basically forces the generator to learn a single deterministic path from noise to data. It's the same property that makes 222-to flow matching so stable.
And the results really speak for themselves. AF models set a new state-of-the-art for single-step generation on ImageNet at 256 pixels, getting the FID down to 2.38. But the really critical thing is that the stability let them train these huge, extra deep models. We're talking up to 112 layers, and they hit an FID of 1.94 in just one forward pass. It suggests model depth, not more steps, is the real key.
Okay, let's unpack all of that. We should probably start with the core problem AF is trying to solve. I mean, we've all seen flow matching models like diffusion just completely take over high-fidelity image and video generation.
They absolutely have. The results are beautiful, the training is stable, but as you said, they're so computationally expensive. You're learning this smooth probability flow, right? Moving from a simple noise distribution to your complex data. But to actually generate a sample, you have to query the network over and over and over again.
Sometimes hundreds of times.
Exactly. And even the attempts to speed this up, like consistency models, still have to train across all the intermediate time steps to get that consistency. It's complex, and you get this accumulated error, which is why GANs were always seen as, like, the holy grail, single-step generation, lightning fast. But they are just notoriously brittle when you try to scale them up to modern transformer architectures.
And that gets to the fundamental question. Why do they break? If you look at the paper's first figure, it visualizes the problem perfectly. The adversarial objective, it only cares that the final distribution of generated images matches the real data.
It doesn't care how it gets there.
It doesn't care at all. So you have infinite possible paths or transport plans from the noise, 6A, to the data, 6Lers.
It's like trying to get a boat from the middle of the ocean, that's the noise, to the coastline, the data. But you don't have a specific dock to aim for. The GAN generator just keeps drifting, taking all these tangled paths because there's no single fixed target.
Precisely. That generator drift is the central instability. Flow matching, on the other hand, it predefines that one clean ground truth probability flow, which gives it stability.
So the breakthrough here is borrowing that one specific deterministic path from flow matching and injecting it into the GAN framework.
That's the core idea. You get the stability of one, but the speed and power of the other.
So how do they actually do that? How do you force a GANs generator to follow a fixed path?
It comes down to some pretty foundational math from optimal transport theory. They use the properties of the 2202 to distance. When you calculate it with linear interpolation and a square distance loss, it naturally defines the single most efficient, lowest cost transport plan.
So it's not some crazy new loss function. They just realize the simplest, straightest path is the most stable one.
Exactly. So they add this crucial optimal transport, or OT, loss to the generator's objective. You don't need to know the exact formula, but what it does is it measures the expected squared distance between the generated sample, GZ, and the original noise, Joseph's fate.
Okay, so the generator is playing two games at once. It's trying to fool the discriminator, but it's also being pulled back toward that mathematically optimal straight line from the noise.
That's a perfect way to think about it. And the effect is huge. The OT loss enforces that deterministic path. It takes away all the infinite bad solutions a GAN could explore and just gives it one good one. It creates a unique global minimum for the generator, which stops the drift.
Looking at the full loss functions, the discriminator one, LDAF, looks pretty complicated. It's got the adversarial loss. Plus, I mean, it looks like every GAN stability trick in the book. 31 and 22 gradient penalties, logit centering.
Yeah, they really threw the kitchen sink at the discriminator.
Yeah.
The takeaway there is that the discriminator needs every regularization trick you can find just to keep it from getting too powerful too quickly and destabilizing everything.
So they basically had to chain down the discriminator.
Right, so that the generator's new OT loss could actually work. And the generator's loss, LGA, is actually very simple. It's just the adversarial loss plus that new scaled OT loss.
And the ablations in the paper really prove how important that little term is.
Oh, absolutely. If you set its weight, lambda to 0, so there's no OT loss. The training just immediately diverges. It collapses.
Wow. So that confirms it. The instability wasn't just some random optimization problem. It was this missing deterministic map.
It really was. But they also found you can't just crank up that lambda value either. If it's too high, it pulls the generated sample too close to the original noise, and you just get, garbage.
But you have to schedule it.
You have to schedule it. You start with a high value to lock in that stable path early on, and then you gradually decay it, letting the powerful adversarial objective take over to handle the fine details of matching the final distribution.
Okay, so you have the math sorted out, but scaling these things up is always an engineering nightmare. What were the big optimization tricks they needed to make this work?
The biggest one, and this is really clever, was dealing with gradient scaling. The gradient signal coming back from the discriminator, its magnitude can be all over the place depending on the model size or how much regularization you're using.
Right, and that would throw off the balance between the adversarial loss and your new OT loss.
Totally. The ratio would be inconsistent. So they introduced a technique they call gradient normalization. It's a component that does nothing in the forward pass. It's just an identity function.
Okay.
But in the backward pass, it normalizes the adversarial gradient to a unit scale using an exponential moving average of the gradient's norm. It's like building a piece of the atom optimizer directly into the backward pass.
So it's an automatic volume knob. It makes sure the adversarial signal is always at the same volume, so to speak, so that the OT signal is always in the right proportion, no matter the model size.
That's it. It makes finding that crucial lambda hyperparameter consistent and reliable.
That is very elegant. And they also showed this whole framework can do more than just single-step generation, right? It generalizes.
Yes, they can do multi-step AF. They just use the standard linear interpolation from flow matching to define intermediate points in time. And the generator learns to jump between any 2 points, say $7.
And they just generalize the OT loss for that, too.
They do. And what's important is that unlike consistency models, they don't need to propagate information across all the time steps during training. It really simplifies the whole process.
Got it. And before we move on, there was this one little detail about the discriminator that seemed really important, a common pitfall.
Oh, yeah, that's a classic one. You must not condition the discriminator on the source sample, so not on the noise Zähler. If you give the discriminator the pair 6x, you're telling it that this one random noise sample, 6xO samples, should be paired with all real data points, 6 Zählers.
Which is an impossible task for the generator.
Impossible. It's guaranteed to cause divergence. So keeping the discriminator in the dark about the specific source noise is critical for stability.
Okay, let's pivot to the results, the actual images, because this is where the adversarial part really seems to beat out the pure L2-based flow models. The paper talks about a congenital defect in flow matching.
Yeah, that's a great phrase for it. The defect is all about that L2 distance minimization at the heart of flow and diffusion models. In a really high-dimensional space, like images, minimizing L2 distance just averages pixels together. It does element-wise blending, not semantic morphing.
So if you're trying to move from a cat vector to a dog vector, the mathematically shortest path is just a blurry, averaged cat-dog hybrid.
Exactly. It's an out-of-distribution, perceptually weird sample. And that's precisely why diffusion and flow models have always needed strong guidance, like classifier-free guidance, CFG, to push the samples away from that blurry L2 average and back onto the sharp, realistic data manifold.
So how does adversarial flow solve that blurriness problem?
Well, by using an adversarial objective, you get a learnable discriminator. It's not a fixed L2 distance. The discriminator is actively learning to spot the difference between real and fake, so it's judging distance based on perceptual and semantic features.
So by fixing the GANs stability, you unlock its natural ability to create sharp, realistic images without needing that external push from guidance.
That's the key. And the proof is in the results for the no guidance setting. The AFXL2 model with no guidance at all gets an FID of 3.98 in one step. If you compare that to a major diffusion model like .ITXL2, it needs 250 steps to get an FID of 9.62.
Wow, a 6-point FID difference is massive. It really shows that the adversarial objective is just inherently better at perceptual quality once you've solved the stability.
It is.
But speaking of a guidance, it's actually really hard to add guidance to a single-step model like this, isn't it? Why can't you just add a classifier loss to the final output?
You can't, because at that final step, the classifier's decision boundary is super sharp. The gradient it gives you is often 0 or just points in a useless direction. It's not helpful.
Okay.
So to get that accumulated gradient effect that CFG gives in multi-step models, they use something called flow-based classifier guidance.
Right. This seemed like a really clever trick. They generate the final sample, and then they interpolate it backwards in time to some random intermediate point, $2 before feeding it to the classifier.
Exactly. You trick the classifier into seeing a slightly noisy intermediate version of the image. That allows it to provide a much smoother, more useful gradient that mimics the effect of CFG, even though the generator itself only ever takes one step.
And the detail there was that the optimal time range, $2, was really small, wasn't it? Something like U 0.1.
Yeah, which is fascinating. It tells you that the AF model generates a really high-quality sample almost instantly. You only need to apply that guidance very early in the implicit flow, which is totally different from diffusion models that need guidance across the whole trajectory.
Let's talk architecture. They really pushed the boat out on model depth, up to 112 layers, just by repeating transformer blocks.
This was a huge engineering win. People have hypothesized that single-step generation needs really deep models, but training them was just too unstable. AF stability is what finally unlocked the ability to train these end-to-end with zero intermediate supervision.
And the deepest one, the 112-layer model, got the best FID of all, 1.94. It even beat its own 4-step version.
And that, I think, is the most important insight for the field. The quality of single-step generation seems to be primarily bottlenecked by the generator's depth and capacity, not the training method itself. We now have a clear path forward. Just build deeper models.
So looking at the final results, AF models are the new single-step champions, and they seem to be much more parameter efficient. Their smaller 130 million parameter model is competitive with consistency models that are over 675 million.
That parameter efficiency is a huge plus, but we do have to be honest about the efficiency trade-off here. AF models train in fewer epochs, so fewer generator updates. But each one of those updates is more expensive because of that heavy, regularized discriminator.
So wait, the paper says the big AFXL2 model uses almost double the training compute of something like AlphaFlow. So are we just trading fast inference for slow, expensive training?
That's a fair point. It is a trade-off. That extra compute is the price you pay for running that very powerful discriminator. But for that price, you get a sample that is 15% better in FID. So if your priority is absolute state-of-the-art quality and single-step inference speed, it's a very favorable trade-off to make.
So at the end of the day, the paper's core hypothesis holds up. You fix the GANs instability with the deterministic flow constraint, and you unlock this incredible perceptual quality and efficiency.
Absolutely. And that final insight that quality scales with depth, even for single-step models, it leaves us with a really exciting question. And this is for you, the listener, to think about. If we can get world-class image generation in one massive, deep forward pass, what does that mean for even harder tasks? I'm talking about video, 3D generation, complex simulations. Does this whole depth over steps philosophy change how we should be building models for things that have complex spatial and temporal components? Can we just bypass all the recurrent steps and do it all in one giant feed-forward map? It's definitely something worth mulling over.